Okay, we are now moving completely into electrical circuits, and we're going to start with a very simple circuit consisting of only a battery and a light bulb, and we're not going to worry about that switch because by now, hopefully you know, the only job of a switch is to create a gap. It's just a wire separator. So shown to the right here is a schematic or an electrical circuit diagram for this very simple circuit. And again, we're not even going to worry about the switch. So what do we need to include? Well, there's a battery here. That is the source of energy in the circuit. And this is how you represent a battery on an electrical circuit diagram. Two parallel lines, one is longer than the other, and the longer line represents the positive side of the battery. Okay, we also have a light bulb, but I don't really want you to think of this as a light bulb per se. It's an energy user in the circuit. And so we're going to call it a resistor, and that is the symbol for any resistor, at least for now. Okay, so what is a resistor? Anything that's going to use energy in your circuit is a resistor. So anything that is going to have charge moving through it, and instead of being a source of energy into the circuit, it's a user of that energy, that is a resistor. And here on the PowerPoint, could be a light bulb, could be a motor, could be a heater, and you can think of anything that uses electrical energy. Okay, now comes the topic of electric potential difference. You think, well, that's just electric potential energy. Well, no, as we talked about with the water circuit, we talked about gravitational potential and gravitational potential difference. That's the change in or difference in gravitational potential energy per unit mass. Well, with electrical circuits, it's a very, very similar idea. Electric potential difference. The difference in electric potential is the difference in electric potential energy at 2 points in your circuit per unit charge. It has the symbol delta V. Remember in our water circuit that the symbol we're using for potential is V. I apologize, I'm not the one who came up with these. And difference in potential difference, of course, is going to have the delta. Oops, we're getting ahead of ourselves. The unit really, let's see, do I have it? Nope. Okay, so for now, I'd like you to think of it as joules per coulomb. Joules per coulomb. Now, why is it joules per coulomb? Because look at the definition for electric potential difference. It is the difference in electric potential energy per unit charge. Okay, that's probably very confusing to you. Here's a more concrete way to think about it. Look at this battery. Look where it's highlighted there. It's a 1.5 volt battery. And here's how you can think about it. In a 1.5 volt battery, the charge passing through the battery gains 1.5 joules of energy per coulomb of charge. So just think about coulomb of charge is a unit of charge. It's an amount of charge. When that amount of charge works its way through the battery, it now has 1.5 joules of energy more than it did at the bottom. And we'll say at the bottom it had no electric energy. When it leaves the battery, it has 1.5 volts of energy, and it's all done per unit of charge. Here's another way to think about it. A 1.5 volt battery does 1.5 joules of work on each charge moving through it. And again, this is a good time to go back to that water circuit analogy. In a water circuit, you were providing the energy to raise the water up to a place of higher gravitational potential energy per unit mass. Although it's hidden in the battery, it's the analogous thing is happening in an electrical circuit. The chemical reactions in the battery are doing work, raising the charge where it doesn't want to go. Charge wants to go from high potential to low potential. And so the chemistry in the battery is forcing it, doing work on it, to raise it from lower potential to higher potential. Here's another way to think about it. The potential difference across the ends of a battery, of a 1.5 volt battery, 1.5 volt battery is 1.5 joules per coulomb. Okay, here's a 1.2 volt battery, which is pretty unusual. It looks pretty darn old, or maybe it's just a European standard. I don't know. Okay, in a 1.2 volt battery, that battery will do 1.2 joules of work on each coulomb of charge moving through it. Or you could say the potential difference created by the battery, or the potential difference across the battery, is 1.2 joules per coulomb. These are 9 volt batteries. Same idea, but now you have different numbers. In a 9 volt battery, or with a 9 volt battery, the battery is going to do 9 joules of work on each coulomb of charge passing through it. Or we could say, actually I'm going this way, it's a little bit more, I mean these are the terminals, but I don't care about the terminals. I just want the imagery to be 9.5, a 9.5 volt battery. The chemistry in the battery will create 9.0 joules per coulomb of potential difference across it. Okay, now we're going to get to the volt thing. Okay, so potential difference is joules per coulomb of charge. However, this guy is Mr. Volta. He invented the first working battery, which is an amazing thing. And in his honor, whoever ran the SI, the International System of Units, said, well, let's name joules per coulomb after him. So they called it a joule per coulomb is called a volt, or a volt is a joule per coulomb, and the symbol is capital V for volts. Okay, how to interpret battery voltage. Okay, now we're into the schematic diagram now. So we don't see a picture of a battery, but we see the symbol for a battery, and next to it is 4.5 V. You should interpret that to mean this is a 4.5 volt battery. Well, here are when I say interpreted, these are some potential different interpretations, and they are all equivalent. You could say, when you see this 4.5 V, you could say, oh, the voltage across this battery is 4.5 volts. Or you could say the potential difference across this battery is, and I should emphasize plus 4.5 volts. Or you could say the potential difference created really by the chemistry in the battery is 4.5 joules per coulomb. And again, it's plus. Or you could say the battery does 4.5 joules of work per coulomb of charge passing through it. These are all equivalent statements. And you really just focus, go back to the water circuit analogy. This is the energy inside of your circuit. This is, chemistry is doing work on the charge, making the charge go from low potential to high potential. And so there is a potential energy per unit of charge difference across the battery. Okay, well, if we have a 5 volt battery and we have a resistor, what's the voltage across the resistor? Notice we're using the term across all the time with voltage. Voltage difference is always going to be across something. I forgot to mention the wires here. Okay, in ideal electric circuits, the wires do nothing except connect the battery, the energy input source, to the energy output source. Or to the energy, the thing that takes the energy. We're going to say that none of the energy goes into the wires. Now that is an idealization, a little bit like the way we say, hey, that book sliding across the table, forget about the friction. It's not important. And so that's what we're going to do with wires. we're going to say that none of the energy put in by the battery is used up in the wires. It all goes to the resistor. Okay, having said that, let's think about conservation of energy. We've got energy coming in that loop rule. Remember, the battery creates a potential difference of 4.5 volts. And guess what? This better be a drop in voltage so that when you go across the entire or through the entire loop, the net change is 0. Or think about the hiker on the closed loop. The net change in gravitational potential energy of the hiker was 0. Okay, well, this is saying in symbols what this wording description says. The potential difference across the battery plus the potential difference across, that is not how you spell resistor, is 0. So let's put some numbers in, and I think you'll see the battery creates a potential difference of 4.5 volts plus an unknown equals 0. Hopefully you see there must be a drop in voltage, or a drop in potential difference, or a drop of 4.5 joules per coulomb of charge moving through the resistor, because these have to add up to 0. So that's the main thing. The voltage created by the battery, or the voltage difference created by the battery, is going to be used. That's what gets used up in a circuit, not the charge moving through it. That never gets used up. Just like water going through a water circuit doesn't get used up. What gets used up, not destroyed, but transferred, is the energy in the circuit. Okay, that's really important that you see that. Energy comes in, energy goes out, but the charge just goes around. Okay, let's finish this section up with just... Wait a second. Oh, I forgot. We have a slide here. Okay, well, what are the different ways we can describe this negative 4.5 volts? Okay, we could say the voltage across the resistor is negative 4.5. Or we could say it's a drop of 4.5 volts. Or we could say the potential difference across the resistor is negative 4.5 volts. The potential difference used by the resistor is 4.5 joules per coulomb. That's okay. Anything that, well, the main thing is to say, look, energy is leaving, and the energy per coulomb leaving is 4.5 volts per coulomb of charge going out, dropping down. Well, the potential difference drops down, the energy goes up. Okay, or we could say the energy transferred to the resistor is 4.5 joules per coulomb of charge. All those are different ways to say the same thing. Okay, now, let's get into some, we were talking about how do we calculate something in a circuit. Well, suppose we have that 4.5 volt battery and we're told there's 0.3 amps going through it. Okay, let's get the power out. Input of the battery, which better match the power output of the resistor, and it will. Okay, so to get the power input of a battery or the output of a resistor, you need to know two things. You need to know the current going through it, and you need to know the potential difference or the voltage difference across it. Okay, here we're told that the current going through the battery is 0.3 amps. And we're told that it's a 4.5 volt battery, so the potential difference or the voltage across it is going to be plus 4.5 volts. Okay, now what I've done in the next line is I basically just want to show you how this all works. Normally you wouldn't have to do this, but I want to remind you that amps is a measure of current, and what it means is coulombs of charge per second. So the current going through this very simple circuit is 0.3 coulombs of charge per second. And the potential difference, the voltage difference across the battery is 4.5 joules per coulomb. Hopefully you'll see that the coulomb here and the coulomb here will cancel, and we're left with joules per second. 1.35 joules per second. And of course a joule per second is a watt. So that is 1.35 watts. That's how you get the power input of the battery, and that's would be equivalent to the power output of the resistor.